Hi everyone. In this video, I will provide you the solution for the second question of the midterm exam that we had. The question is here. We have a block diagram of the process GP, in which we have the input to the process U and we have the output of the process, and there are some blocks in between. And we will have the GP in the form inside the feedback loop with the unity negative feedback and the proportional controller as provided as the KP. And here are the questions. We want to find the transfer function of the process GP. We need to find the steady state error for unit step, unit ramp, and unit parabola references when we have KP equal to 10. We need to draw the root locus for KP in R and discuss the stability. And at the end, we need to compute the value of KP such that two poles of the closed loop system are on the imaginary axis. And then we will see if it's reasonable to find the location of the imaginary poles for the system. So let's start with the first point. We want to find the transfer function of the process. We have here the block diagram of the system. As we can see here, the two blocks that we have here, the 3 and 4 over S, are in parallel with each other. So they could be replaced with one block with a, let's keep the positive sign here. So we will have 3 minus 4 over S. And here we have the output C. And 3 minus 4 over S could be rewritten as 3S minus 4 over S as well. Then we have this block here, 1 over S. This could be moved outside. Maybe I will just redraw everything here. So we have the input U 1 over S. We have 3 with negative feedback, 1 over S, 2 with negative feedback. Then we have what we have obtained, 3S minus 4 over S. And from here we have 1. And then they are added to each other to provide us the output. So if we move this 1 over S to the other side, what we end up is like this. U 1 over S. So we have 1 here. We have 3 with the negative feedback. 1 over S moves to the other side. So we will have 1 over S. And from here we have 3S minus 4 over S. 1 over S move appears here as well. So we will have 1 over S times 2 or 2 over S with the negative sign of the feedback here. Now, as we can see here, these two blocks are in series with each other and the whole thing here are in parallel with each other. So what do we have here is 3S minus 4 over S squared. And we have 1 over there. So the whole thing here will be equal to 3S minus 4 over S squared plus 1, which is equal to S squared in the denominator and S squared plus 3S minus 4 in the numerator. And here we see that these two branches are in series, in parallel with each other. So we will have 3 plus 2 over S, or 3S plus 2 over S. And we have the feedback configuration. So 1 over S, 3S plus 2 over S with the negative sign. And then afterwards we have the s squared plus 3s minus 4 over s squared, and we will have the output. Now we just need to find out the equivalent of this feedback loop here. We will have 1 over s over 1 plus, since we have a negative feedback, we will have 1 plus 1 over s times 3s plus 2 over s. We will have 1 over s. At the denominator, we will have s squared plus 3s plus 2 over s squared. And finally, we will have s over s squared plus 3s plus 2. Therefore, from u towards the output of the process, we have two transfer functions in series with each other. S over s squared plus 3s plus 2 and s squared plus 3s minus 4 over s squared. And as a result, the transfer function from the input of the plant to the output will be equal to s squared plus 3s minus 4 over s times s squared plus 3s plus 2. So this is indeed the solution for the first part of the question. So now we have GP. We are done with this part. Let's see what do we have for the next part. We need to find the steady state error for unit step, unit ramp, and unit parabola references when Kp is equal to 10. So we have Gp equal to s squared plus 3s minus 4 over s times s squared plus 3s plus 2. And Gc, the controller, is given as Kp. As a result, L of s, the loop transfer function, is equal to Kp times s squared plus 3s minus 4 over s times s squared plus 3s plus 2. And we have Kp equal to 10 here. Looking at the L of s, we see that it is a type 1 system. We have a type 1 system. And we know that for type 1 systems, steady state error for unit step is equal to 0. Steady state error for unit ramp is equal to 1 over kV, and steady state error for the unit parabola is infinity. So we need only to find out kV and determine the steady state error for the unit ramp. We know that kV is equal to limit of s times L of s as s goes towards 0. We will have limit of s times L of s is given here. So we have 10 times s squared plus 3s minus 4 over s times s squared plus 3s plus 2. As s goes towards 0, we will have kV equal to minus 40 over 2 or minus 20. As a result, steady state error for unit ramp will be equal to 1 over minus 20 or minus 0.05. And we are done with all the three steady state values of the errors or steady state errors for 3 different cases. Okay, so this means that we are done with the second section of the question. In the third section, we need to draw the root locus for Kp in R and discuss the stability. So we have Gp given in this form. Let's start plotting the root locus. For Kp in R. So we just set the value of Kp equal to 1, draw the root locus, and then we can discuss based on the different values of Kp. We have L of S equal to, keeping Kp equal to 1, S squared plus 3s minus 4 over s times s squared plus 3s plus 2, and we can rewrite it in the form of s plus 4 times s minus 1, and in the denominator we will have s times s plus 2 times s plus 1. So this means that in terms of the location of the poles and zeros of the system, we have 1 0 at 1, 1 0 at 4, one pole at the origin, one pole at -1, and another pole at -2. And for this, we will draw the root locus. So let's start to see if we have any asymptote or not for this system. We have n equal to 3 number of poles and m is equal to 2 number of zeros. So r, which is equal to n minus m, is equal to 1 number of asymptote, which means that we have 1 asymptote. So for this asymptote, we can find out xa, which is equal to sum of zi's minus sum of pi's over n minus m, which is 1 in this case. So for sum of zi's, we have 4 minus 1, minus for sum of pi's, we have 0 plus 2 plus 1 over 1. As a result, xa will be equal to 3 minus 3 or 0. We can find the angle of asymptote. We have only one asymptote, so the angle of asymptote will be equal to 2h plus 1 times pi over n minus m, which is 1, so there's no need for writing it, and 2h pi for the negative locus. Since we have only one asymptote, h will be equal to 0. Therefore, KCA will be found as pi and 0 for the positive locus, for the negative locus. So now we have the asymptote. Let's start to draw the root locus by providing two plots here. For the positive locus and another graph for the negative locus. Determining the location of the open loop poles and zeros, we have 1 0 at +1, one pole at origin, one pole at -1, one pole at -2, and the 0 at -4. And the same thing here, 0 pole, 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 and another 0. So we can determine which parts of the real axis belong to the root locus, parts of real axis. We have different segments here, from -infinity to -4, from -4 till -2, from -2 till -1, from -1 till 0, 0 till 1, and from 1 till infinity. We can count the number of poles and zeros on the right hand side of any test point in these areas. So starting from this point, we have from 1 to infinity, we have 0 number of poles and zeros on the right hand side. For this area, we have 1. For the area between -1 and 0, any point here, we have 2. We have 3 here, 4, and 5. The ones which are odd belong to the positive locus. So this area belongs to the positive locus, this belongs to the negative locus, positive locus, negative locus, positive locus, and negative locus. And we can show them on the on the graphs as well. From minus infinity till minus 4 belongs to the positive locus. So this section of the real axis belongs to the positive locus, this section as well, and this section. And for the negative locus, we have this section here, this section on the real axis, and this section. So we are done with determining which parts of the real axis belongs to the root locus. As the next step, we can find out the break-in and breakaway points for this system. So break in and breakaway points. So again, we need to have L of S as we have here. Let's write it again. L of S is given as S squared plus 3S minus 4 over S times S squared plus 2S plus 3S plus 2 plus 3S plus 2. So from here we have N given as S squared plus 3S minus 4 or S plus 4 times S minus 1, and D of S is provided as S times S squared plus 3S plus 2, or in the form of S times S plus 1 times S plus 2. And what we need to do here is to find out M prime D minus D prime N equal to 0, and from there we found the roots, and those roots could be the break-in or breakaway points for us. So let's see if we can find them in it easily or in the straightforward way. M prime will be equal to 2S plus 3, and D prime will be equal to, so S times this, and then deriving it, we will have 3S squared plus 6S plus 2. Replacing this into the equation, we will have M prime times D, so 2S plus 3 times S times S squared plus 3S plus 2 minus D prime, which is 3S squared plus 6S plus 2 times N, which is S squared plus 3S minus 4 equal to 0. So looking at this, we see that we have a fourth order polynomial here, and we have a fifth order polynomial here. So in general, we will have a fifth order polynomial, which will have 5 roots. And I think that it's not very easy to solve it for all the roots here, for this polynomial. So let's see what we can do in it. Having a look at the root locuses in terms of the segments of the real axis that belong to our root locus, and the idea that the branches will start from the poles and they will go towards the zeros, and one of them will go towards infinity using the asymptote that we have, we can guess some zones on the real axis which will have the break-in or breakaway point on them. So indeed here we can also plot the asymptote. I will do it right now. For the asymptote, we have xa equal to 0 and the ca equal to pi and 0 for different cases. So here we will have asymptote starting from 0 and going towards minus infinity for the positive locus. And for the negative locus, it will start here and it will have the angle of 0. So this will be our asymptote. Now looking at the positive locus, We have one pole at the origin and 1, 0 on the right hand side, and there will be a branch starting from this pole going towards that 0. So this will be indeed one of the branches. We have this segment belonging to the root locus, so we will have these poles, the branches starting from the poles, they will come towards each other, and at some point here, which is not known for us, and it's one root of the m prime d minus d prime n, they will depart their real axis. Since this segment of the real axis belongs to the root locus, and there is a 0 here, we know that one of the poles one of the branches will arrive at the 0 as the value of k goes towards infinity. And since we have an asymptote here going towards minus infinity on the real axis, we will have another branch going towards minus infinity. So it's obvious that there should be a break in point at some point on the left hand side of the minus 4. So we will have something like this for the positive locus. But again, keep in mind that these points, these 2 points, the break-in and breakaway points, are not known for us. They are the roots of m prime d minus d prime n, but for now we just can think that they are somewhere over there. So it's especially they are not very important here because they don't affect the stability of our system. But if you want to have the exact root locus plot for this system, we need to find the break-in and breakaway points. So now let's have a look at the negative locus. So we see that we need to have a branch going towards plus infinity on the real axis, since we have an asymptote. So there will be a branch here, and there will be a branch coming towards the 0 on the 0, which is located at 1. We have 2 branches departing from the poles at 0 and at minus 1. They will come towards each other, and they will depart at some point their real axis. So there should be a breakaway point here. Between 0 and minus 1. Then looking at the other segment here, we see that this segment belongs between minus 4 and minus 2 belongs to the root locus. We will have a branch originating from minus 2, and it will arrive at the 0 at minus 4. So this means that we need to have branches departing from a breakaway point, and they will arrive at the real axis on the right hand side at some point. So here we will have a break in point. So again, the value for the break-in and breakaway point, the exact value is not known for us because we didn't solve the m prime d minus d prime n equal to 0. But at least we know that it should be somewhere on the right-hand side of 1. And the breakaway point will be somewhere between 0 and minus 1. So this is the somehow the rough root locus plot for this system. And you can see that in this case, we don't really need to calculate the angle of departures and the angle of arrivals because they are trivial for us. All right, so I can say that we are somehow done with drawing the root locus, but we need to discuss the stability. And we need to find out for which value of Kp the closed loop system is stable. So looking again at the root locus plots that we have, here we have k bigger than 0, and here we have k smaller than 0. And we can see that for k bigger than 0, we always have a pole on the right-hand side of the j omega axis. So in this case, we see that the closed loop system is always unstable. Looking at the negative locus, we see that starting from k equal to 0 and going towards minus infinity, for the values of k starting from 0 and moving towards minus infinity, at some point for some value, we will have our system stable because we will have two poles here and one pole somewhere around here. So we can say that for Kp is smaller than 0 and bigger than alpha, a parameter which is smaller than 0, the closed loop system will be stable. Otherwise, if Kp is smaller than alpha, the closed loop system will be unstable. So this is what we can conclude about the stability. We just need to find out the value of alpha or the critical Kp for which our system becomes critically marginally stable. And that's indeed what we do for the last part, because we need to find out the value of Kp such that the poles of the closed loop system are on the imaginary axis. And indeed, in that case, we will have the marginally stable system. So let's see how we can find the value of the alpha. One way to do it is to use the Ross-Horowitz criteria. We can form the Ross table and find out the value of Kp for which we are at these points. So let's do it maybe here. We have 1 plus Kp times s squared plus 3s minus 4 over s times s squared plus 3s plus 2 equal to 0 as the characteristics equation. From here we will have s times s squared plus 3s plus 2 plus Kp times s squared plus 3s minus 4 equal to 0. And then we will have s to the power of 3 plus 3s squared Kp s squared 3 plus Kp s squared plus 2s 3 kps 2 plus 3 kps minus 4 kp equal to 0. This will be the characteristics equation for which we can form the Ross table. To form the Ross table, we have S3, S2, S1, and S0. For the first two rows, we have 1, 3 plus Kp, 2 plus 3 Kp, and minus 4 Kp. And we need to fill the rest of the Ross table. We need to find the value for this element. Here we will have 0. And for the last element, we will have minus 4 times Kp. So the only missing one is here. And to find the value for that, we need to find out the determinant of 1, 3 plus Kp, 2 plus 3 Kp, and minus 4 Kp divided by 3 plus Kp. So keeping this in mind, we will see that if Kp is such that this is equal to 0, we will have a complete row equal to 0. And this means that we will have poles on the j omega axis. So let's see how we can have this situation. So we need to have determinant of 1, 3 plus Kp, 2 plus 3 Kp, and minus 4 Kp equal to 0. We will have minus 4 Kp minus 2 plus 3 Kp times 3 plus Kp equal to 0. Or multiplying everything by a negative sign, we will have 4 Kp plus, so we have 6 plus 2 Kp plus 9 Kp plus 3 Kp squared equal to 0. Or we will have 3 Kp squared plus 4 to 9 or 15 kp plus 6 equal to 0, or in other words, kp squared plus 5 kp plus 2 equal to 0. We need to find the roots of this second order polynomial. Kp will be equal to minus 5 plus minus square root of 25 minus 4 times 2 over 2, or minus 5 plus minus square root of 17 over 2, for which you can find the answers. And the answers are kp1 and kp2. We have two answers indeed. One is minus 4.5 and minus 0.439. So we have two values, but which one is the valid one? So we cannot have both of them valid in this situation. So let's see which one of them is the correct one. We can refer to our root locus table as well. So from here we can see that if we want to have our system stable, we need to have kp smaller than 0 and bigger than alpha, and alpha is one of these two i's. So if we set alpha equal to minus 4.5, what happens is that here this 3 plus kp will become negative, and it means that our system is not stable. So to have the system stable, we need to have 3 plus kp smaller than 0. We need to have minus 4 kp, bigger than 0 in both cases, because we don't want to have the change of the signs. Yeah? From these two, we get kp should be bigger than minus 3, and kp should be smaller than 0, as we already know. And as a result, we can see that this value here wouldn't be a proper one, because it doesn't satisfy this. So we see that the final result is kp equal to minus 0.439, in which we have two poles on the j omega axis, and our system is marginally stable. So then, as the last part of the question, we need to find the location of the poles in this situation. So one way to do it is to refer to the characteristics equation here, replace k with minus 0.439, and then solve this. We will have two roots of the system will be s equal to s1 equal to j omega, s2 equal to minus j omega, and we will have the third root between minus 2 and minus 4. So the s3 will be between minus 2 and minus 4. That's one way of finding the value for the s. And as another solution, you can replace s with j omega, k with minus 0.439, and then find the characteristics equation equal to 0, for which the real part and the imaginary part should be equal to 0. So let's do it together. We have s to the power of 3, replacing it with j omega, we will have j omega to the power of 3 plus 3 plus kp times j omega squared plus 2 plus kp times j omega minus 4 kp equal to 0. And we can rewrite j omega to the power of 3 equal to minus j omega to the power of 3. J omega squared will be equal to minus omega squared. So minus omega squared times 3 plus kp plus j omega times 2 plus kp minus 4 kp equal to 0. And now we can divide this into the imaginary part and real part. We will have j times omega 2 plus kp minus omega to the power of 3. So these two terms here minus 4 kp plus omega squared times 3 plus kp equal to 0. And since we want the whole thing be equal to 0, we need to have this equal to 0 and this term equal to 0. So from here we have omega squared equal to minus 4 kp over 3 plus kp, and as a result omega will be the square root of minus 4 kp over 3 plus kp. And from here we have omega equal to 0, which is what we get for kp equal to 0 as well. And on the other hand, we will have omega squared equal to 2 plus kp, or omega equal to square root of 2 plus kp. From any one of these two, by setting kp equal to minus 0.439, the exact value of kp indeed, we will get omega equal to 0.8274. So this is the value for the pose on the j omega axis. Okay, so therefore we are also done with this segment. Where are these poles located on the imaginary axis? We already know. Indeed, if you want, you can find the location for the third pole as well, which is somewhere around here. If you apply the amplitude criteria, you know the value of kp, the corresponding value of kp, you know the location of the poles here, and then you can easily find the location of the pole, the third pole, but it's not part of the question, so I will not go through it. All right, so this is all for this question. We did all the parts together. What we didn't find precisely was the points of break in and break away that we had for two cases, as these 4 points, but you can see that they are not that important here in terms of determining the stability of the system based on the value of the k. So that's fine for now. Otherwise, we would need to find the roots of the fifth order polynomial, maybe using some tools. All right, so thank you for watching and see you next time.